Assalamu alaikum. Now today we'll study about the Norton's theorem. In previous classes we studied about the superposition theorem, source transformation and Thevenin's theorem. So in this chapter another two topics left out, Norton's theorem and maximum power transfer theorem. So Norton's theorem. So in this Norton's theorem the definition will be Norton's theorem states that a linear two-terminal circuit can be replaced by an equivalent circuit consisting of current source IN in parallel with the resistor RN, where IN is the short circuit current through the terminals and RN in the input or equivalent resistance at the terminals when the independent sources are turned off. What it means here? It means same like a Thevenin's theorem, we had source that is called Thevenin's voltage and a in series resistance R Thevenin's we used to have with the load where we want to get the result, where we want to see the behavior. Here, like a source transformation, when the Thevenin's voltage source and the in series Thevenin's resistance, when it we converted to current source, then as per the source transformation, it become Norton's current source and in parallel Norton's resistance. So based upon the source transformation, the R Thevenin's and R Nortons both are same because it's like a same thing. Source transformation method if we use, RN will be and R Thevenin's will be same. Only it will be because of the linearity, it will be changed in voltage source to current source. But the method is same, or how the V Thevenin's is calculated, Thevenin's voltage. Here Norton's current also calculated with the same rules. We'll see those rules now. The Thevenin's and Norton resistance are equal. That is Rn is equal to R Thevenin's. See the circuit. This is a linear two-terminal circuits between terminal A and B, left side. That is on the left side. Whatever the big circuit is there, we have to merge it, or we can make it equivalent to one resistance and one current source. So whatever the equivalent resistance is there, that is called Norton's resistance, and also it is equal to Thevenin's resistance. Both are same. If you are calculating Thevenin's, then which is also equal to Norton's resistance. Same procedure, same steps, everything will be same. Now to find the Norton's current, we determine the short circuit current flowing from terminal A, B in the both circuits. So we have to find the terminal current in both A and B. We have to short circuit these two, and then we have to find the current in it. Okay, see the resultant circuit here. It is a Norton's source, and this is the Rn, Norton's resistance, which is also equal to Thevenin's resistance with same terminal A and B. This linear is equivalent to with this source current and a parallel resistance. It is obvious that the short circuit current is IN. This must be the same short circuit current from the terminal A and B in the figure A. Since the two circuits are equivalent, thus IN is equal to ISC. So this IN is nothing but what the current is flowing in A and B, that is ISC, short circuit. We have to make the short circuit and we have to find the current flowing between A and B. So which is equal to IN. Dependent and independent sources are treated the same way as Thevenin's theorem. Dependent and independent sources are treated same way as Thevenin's theorem. So when dependent sources are there, some rules we followed in Thevenin's theorem. If independent sources are there, we followed some rules to find the R Thevenin's or to find the V Thevenin's. Here also same rules we have to follow for finding the R Newton, or what we call Nortons and I Nortons, current Nortons. We'll see that one. The Thevenin's and Norton's equivalent circuits are replaced by a source transformation. What I told you in previous, we can replace it by a source transformation. So if a Thevenin's equivalent circuit is given to you and ask for the Norton's equivalent circuit, then just use the source transformation, that is V Thevenin's divided by R Thevenin's, that is become the IN. Now R Thevenin's will become Rn, which will be in parallel with the current source. to the close relationship between Norton's and Thevenin's theorem is Rn is equal to R Thevenin. Both resistances are equal. So next, then In will be nothing but V Thevenin's by R Thevenin's. So as per the Thevenin's equivalent circuit, the Norton's current In will be V Thevenin's by R Thevenin's, and R Thevenin's is also equal to Rn. So we can replace this one. Same procedure. If you don't know the Norton's current, how to find, you don't know the how to find the Norton's resistance. If you know only the Thevenin's, then you can find with the Thevenin's rule, which is also same for the Nortons also. But if you have practiced with the Thevenin's theorem to find the V Thevenin's and R Thevenin's, then find it first. Then by using the source transformation technique, In is equal to V Thevenin's by R Thevenin's, you will get the In. Then R Thevenin's will be Rn, which is also equal. Okay. Now next. So already we know In is V Thevenin's by R Thevenin's. Since In and V Thevenin's and R Thevenin's are related according to this equation, to determine the Thevenin's or Norton's equivalent circuit requires that we find In is equal to V Thevenin by R Thevenin's. So what we have to find? The open circuit voltage across A and B we have to find. Then the short circuit current at the terminals A and B. Next, to the equivalents are input resistance at terminal A and B when all independent sources are turned off. So when independent sources are there, they must be turned off. What is the independent sources turned off means? Any voltage source, independent voltage source, any voltage source which is independent, we have to short circuit. Any current source, independent current source, we have to open circuit. So like this, we have to find the input resistance between terminal A and B, which is equal to R Thevenin's, or which is equal to R Norton's. Both are same. So we can calculate any two of the three using the method that takes the least effort and use them to get the third using Ohm's law also. That is, in these three methods, any one you can use, and the third one is the best one, that is for the finding the resistance. Now we can write the three equations. What is V Thevenin's? It is VOC by using the first method, that is open circuit. Next, In by short circuiting the A and B terminals, we will get the In, that is ISC, and VOC is V Thevenin's. Now we know the third, we don't want to do the third one, the equivalent input resistance. You want to skip this one, you can directly find with R Thevenin's by V Thevenin's divided by In, that is also known as VOC by ISC. So directly you will get the R Thevenin's or Rn, both are equal. So use the step 1 and step 2, we will get all the three items. No need to go for the third one. Or use step 1 and step 3, you can find the step 2 also. Or use step 2 and step 3, you can find the step 1 also. So like this, we have the options. The open circuit and short circuit test are sufficient to find the Thevenin's and Norton's equivalent of a circuit which contains at least one independent source. So we have to see that on the left hand side, it must have one independent source minimum. If more dependent are there or other sources are there, more sources are there, no problem. But the Norton's theorem and Thevenin's theorem always is calculated with a source inside that linear circuit between the terminals A and B on the left side. Some example Norton's theorem. Find the Norton's equivalent circuit of the circuit in figure 4.39 at terminal A and B. What is the circuit? This one. See, I told you minimum one independent source should be there, but here we have two independent sources. One is voltage source, one is current source. So we need a equivalent Norton's equivalent circuit between terminal A and B. So what we need? We need a I Norton's and R Norton's, also equal to R Thevenin's. Anything you can find. So now what we do, we can just find the R Norton's or R Thevenin's by what we have to do. We have to switch off the independent sources. Switching off the independent sources means what? We have to short circuit the voltage source, open circuit the current source. So short circuit this 12 volts voltage source, 4 ohms only will left out in this branch. 4 ohms only left out. Remaining all are the resistances. Now open circuit this current source, then it will be open here. So these 4 ohms and sorry, this 4 ohms, 8 ohms, and this 8 ohms here. 4 ohms, 8 ohms, and 8 ohms will be in series because this is open circuit now. So this is in series, then 5 ohms will be in parallel. That is your result for the R Nortons. Very simple. So 5 ohms is the parallel with the series of 848. 848. That is, these are the in series. So 848 become 20 and 5 ohms is the this resistance which is parallel. So 5 ohms and 20 ohms in parallel is 20 into 5 divided by 20 plus 5, 25, which is equal to 4 ohms. Now we got R Nortons, which also equal to R Thevenins, which is 4 ohms. So only we have to find IN. That is Norton's current. For that, we have to, what we have to do? We have to short circuit this A and B terminals. And what is the current flowing between A and B terminals? We have to find. For that, we need 1, 2, 3 loops. Then we'll see. So the problem here is now when we short circuit terminal A and B, what's happening? Because of the short circuit, this resistance will come out because the current will always take low resistance path. So in this, zero current will flow in 5 ohms resistance because there is a zero resistance circuit is here, path is there, silk is there. So here complete current what is used to flow in 5 amperes will flow here. It may be more or less, but the 5 amperes is now nullified. You cannot take it into picture. Okay, so now we have one loop, this one, which is I1, which is also equal to 2 amperes, and another loop in between 4 ampere, 4 ohms, 8 ohms, 5 ohms is not in the picture, then 8 ohms, then 12 volts. This is another loop. So write the Kirchhoff's mesh analysis, Kirchhoff's voltage law, KVL. Now I1, so first loop I1 is 2 amperes as it is. Now the second loop. In the second loop, what we have to start with, we can add up all the resistances where I2 is flowing. That is 8, 4, and 8. So 8, 8, 16, and 4, 20. 20 ohms into multiplied by I2 minus I1 because 4 ohms I1 is there. I1 is flowing in the 4 ohms only. So minus 4 I1, and current is leaving from this I2 is leaving from the 12 volts. It's a battery. So it is minus 12 equal to 0. This is the one. For equation, and I1 already we know 2 amperes. Substitute in this, you will get the I2. So we actually need I2, which is also equal to ISC, which is also equal to IN. So directly you got I2 1 ampere. If you substitute in this, then 1 ampere ISC is same and IN is also same. So we have another method for finding that I short circuit, that is IN, that is by using voltage VThevenins. Once you find the VThevenins by source transformation also we can get the IN. That is VThevenins divided by RN, you will get the IN. So for VThevenins, what we have to do? We have to open circuit that circuit, the given circuit in terminal A and B, and apply the loop analysis and find the what is the voltage between A and B. So we have two loops now. One is I3 and I4 because already I1, I2 I used. So I use the next terminology I3 and I4. So I3 is always equal to 2 amperes because in this loop current source is there. So I3 is always 2 amperes, same direction. Now another loop, we have Kirchhoff's voltage law, another loop, that is all resistances we can add 8, 8, 16 and 4 to 20, and this is 25. So 25 I4 minus 4 I3 and minus 12 equal to 0. I3 is 2 amperes. You can write another equation, minus 25. All resistances together, I4 is flowing. So all resistances are in series. So as per the loop, so 25 I4 minus 4 I3. In the 4, I3 is also flowing, which is opposite direction, minus 4 I3 minus 12. Current leaving the voltage source, minus 12 equal to 0. I3 already you know, so I4 you can substitute. I can be calculated by substituting I3 2 amperes in this equation. I4 will be 0.8 amperes. So what is I4 here? So once you know the I4 here, the voltage across terminal A and B is nothing but this I4 multiplied by this resistance V is equal to IR. So we can find what is R? 5. What is I4? 0.8. So 5 into 0.8, it is 4 volts. So previously also we got previously not we got, now we got VThevenins 4 volts. Now once we got VThevenins as a R, which is equal to VOC 4 volts, IN will be VThevenins divided by RThevenins. So RThevenins also we got 4 ohms, and this is VThevenin we got 4 volts. So 4 by 4, 1 ampere, which is the same as the previous case what we calculated IN. So VOC is equal to VThevenin, which is nothing but 5 times I4, that is 4 into 0.8, that is 5 into 0.8, it is 4 volts. Now find IN. So IN is nothing but VThevenin by RThevenin. VThevenin 4 volts and RThevenin what we calculated in first step, that is 4. So 1 ampere, same case that is. Now this is your equivalent Nortons. 1 ampere is the current and 4 ohms is in parallel. R Thevenins are R Nortons. So this is your answer. Now we will go for the another example with the dependent source. So dependent source, now let us take this is the example. So this is the another example. Now we have to find Rn and In between terminal A and B. So these are the terminal A and B. We have to find IN and Rn. Now there is a dependent source whose current is depending on this branch 4 ohms Ix. Now what we have to do, first check this first circuit. In this first circuit, because it's the dependent source, how to find the R Thevenins or R Nortons? We have to apply some voltage or some current here in between terminal A and B. So I am applying first step voltage. Let us take later. Another method also there. IN also we can apply. That is 1 ampere also, but better go with the voltage source with 1 volt. So I am applying a voltage source in between 1 volts to find the R Thevenins or R Nortons. So for that, now check it here. When it is given the 1 volt, we have to find the loop. So Rn will be nothing but V0 by 0. What is Rn? R Thevenins or R Nortons? V0 by what are the voltage here divided by I0. That is voltage already there. 1 divided by I0. 1 divided by I0. What is the current here? How much current is flowing here? How can we find? So now to find an independent voltage source equal to 0. Okay. Now V0 is 1 volt already we applied here. Okay. Now we obtain in the circuit, we ignore 4 ohm resistance. This 4 ohm resistance we ignore. How? Why you are ignoring? Because this voltage source, as per the independent source making 0. So this will become short circuit. We become 0. So it becomes short circuit. If it is current here, we can open circuit that one. Means we have to make sources off, switch off. So this becomes short circuit. When this is short circuit, the current will take a low resistance path. So this 4 ohms will be eliminated. The current will not flow here, only it will flow here. So Ix will become 0. When Ix will become 0, this also becomes 0. So these both branches now nullified. Now the resultant will be this one. This is the one. Only this one. So only 5 ohms. The resistance will be 5 ohms. Now this is the 5 ohms resistance will be there. Now the current will be I0, which is equal to 1 volt divided by what we are giving, current what we are giving, 1 volt divided by this 5 ohms. So 1 divided by 5 ohms is nothing but 0.2 amperes. So once the the 0.2 amperes is the current, what is the Rn? Which is V0 divided by I0, we know that is also equal to 1 divided by 0.2, that is 5 ohms. So this 5 ohms also act is nothing but your resultant Thevenins or Norton's resistance. Okay, now we have to find what is the short circuit current. To find IN, we short circuit terminals A and B and find the current ISC as indicated. Note that from this figure, the 4 ohm resistance. Now what's happening to 4 ohm resistor? The 10 volt voltage source, the 5 ohm resistor, the 10 volt voltage source and 5 ohm resistor and dependent current source. Then dependent current source are in parallel. See the node analysis. Yeah, this is the parallel to this one. And when it is short circuited, you can tilt this one. Then 5 ohms will also in parallel with this voltage source and 4 ohms. Same, to Ix is parallel with 5 ohms. We have to connect this to this node here. A and B is short circuited both together. So what's happening? The current at the entering node Ix is also known as, what is Ix? It is the same voltage what it is there. It will be this branch, and same voltage it will be in this branch from this point to this point. The same voltage will be in this branch. So what is Ix? I is nothing but this 10 volts divided by 4. 10 volts divided by 4, 2.5 amperes. Now once you know the 2.5 amperes, here you know what is the current source. 2 into 2.5, 5 amperes is the current source. Okay. Now what is the current in this branch now? Because voltage, voltage in this branch again, it is 2 into 5, 10 volts. Same 10 volts it is. Okay, now we'll find the what is IN. Now at node analysis KCL at point A, what ISC is nothing but our current is leaving. Current leaving in at this node is nothing but two currents are entering. Okay, one is 2Ix and another is higher potential to lower potential, right? This is the higher potential, so then lower potential. So minus of minus, it is 0. We don't know here. So 0 plus minus of minus plus 10. So 10 divided by 5. Higher potential is 10. So minus here 0 here. We don't have any voltage because it is a short circuit. So it is 0. So 10 minus 0. So 10 divided by 5 ohms is the resistance. This current is entering at this node. Now this current entering this node is 2Ix, that is plus 2Ix, that is entering, which is equal to current leaving at this node, that is ISC, which is also equal to IN. So find that one. 10 by 5 is 2 and 2Ix. Ix already we find 2.5. 2 into 2.5 it is 5. So 5 plus 2 it is 7. So 7 ampere is your IN. So we got the IN and we got the RN. So we got 7 amperes is the current and 5 ohms is the RN. We can have the equivalent circuit. Now coming the maximum power transfer. So last topic in this chapter, maximum power transfer means at what point the circuit behaves like it is getting a maximum power in the complete scenario. In many practical solutions, a circuit is designed to provide a power to the load. The load resistance between terminal A and B on the right hand side is a load resistance generally. So in that resistance, we have to deliver maximum power. So how it can possible? There are applications in areas such as communications where it is desirable to maximize the power delivered to a load. Means in communication networks, we always think about the power should be delivered maximum during its working. So how to find that one? The Thevenin's equivalent is useful in finding maximum power a linear circuit can deliver to a load. So we have two options, Thevenin's and Nortons. So Thevenin's always is useful to finding the maximum power. If you have Nortons also no problem, but you have to, so by using source transformation, you have to convert to Thevenin's, then you can find the maximum power. Easy, because in the Thevenin's, the voltage source will be in series with a Thevenin's resistance and the load also in series. So all are in one loop only. In Nortons, there will be two loops, source current and Thevenin's or Norton's resistance and the load resistance. So the calculation will be quite bigger than the Thevenin's. So let's go with the Thevenin's one. We assume that we can adjust the load resistance. No, every time now change the load resistance so that we can see when the power is maximized. If the entire circuit is replaced by its Thevenin equivalent except for the load as shown in figure, the power delivered to the load will be. So now we just, this is the load resistance where we want to vary every time, so that we have to find at what point the power is transferred maximum. So now on the left side between terminal A and B, we equalize with the Thevenin's voltage and Thevenin's resistance. Now vary the RL. Now as per this loop, what the equation we can write for the power? I square R in this current. What is the power in the resistor RL? Is nothing but I square into RL. There is the power delivered to this resistance, power equation. Or VI also you can put, and V is nothing but VI also you can use, VI into R you can put. So I square R will come, I power 2 and RL. Now what is I? So what is I in this? Is nothing but voltage division rule we can use. What is I? Voltage division rule. It is total voltage multiplied by the same resistance, where we want to find the I, divided by the total resistance. So total voltage divided by the total resistance multiplied by RL. That is your complete this one. So I is nothing but V Thevenin's. What is the current? V Thevenin's divided by R Thevenin's plus RL. Right? V Thevenin's divided by R Thevenin's is the current, because it's one loop only. This is one loop. All these two resistances are in series. So V Thevenin's by R Thevenin's plus RL is nothing but your I. So it is power 2 multiplied by RL. That is resistance in where we want power. So that resistance we apply I square R, then it is your power. Now when it will be the maximum power? So just increase the RL every time, then which is equal to R Thevenin's. Then it become 2 times RL. So 2 times R Thevenin. Let us take RL when become R Thevenin, it become 2 times R Thevenin. Here also R Thevenin. 1 V Thevenin's power 2 divided by 4 times R Thevenin's power 2. So 1 R Thevenin will cancel. It become V Thevenin's power 2 divided by 4 times R Thevenin. We'll see that one. So maximum power is transferred to the load when the load resistance equal to the Thevenin's resistance as seen from the load RL and R Thevenin. From seeing this time, I am varying the RL so that when it will be maximum, when these two resistance are equal, then only the current will be the maximum. When current is maximum, power is maximum. So when these two are equal, then only maximum power is transferred. So now see, we will see the graph also how it is there. For a given circuit, V Thevenin's R Thevenin's are fixed. We cannot change because the circuit is fixed one. By varying the load resistance, the power delivered to the load varies as shown in the sketch. 4.49. See here, this sketch, you can see the variation. This is the RL on the x-axis and the y-axis is the power, how it is transferred. Now, change the resistance RL because RL will increasing here every time. Then the power will increase, right? P square, then when RL is here and here, both are there. When RL I am increasing, here power is there. So it will increase up to the point maximum RL is equal to R Thevenin's. Then it will decrease again. If you want, you can have some 5 or 6 step values of RL, we can find which is equal to R Thevenin's and which is less than RL and which is greater than R Thevenin's. Less than R Thevenin's, 1 point you can use, and greater than R Thevenin's you can use another point. See the power calculation. It will be equal maximum at R Thevenin's is equal to RL. Okay, you can find out, no problem. In example also we can show it. So at the point where RL is R Thevenin's equal, then at the point only the power is maximum. This graph is very important. Maximum power transfer graph. You can, if you ask to draw, you can have to draw this one. Now we notice that the power is small for small or large values of RL, but maximum for some values of RL between 0 and infinity. Between 0 and infinity will be very small, but here it is maximum. Now let us see. We now want to show that this maximum power occurs when RL is equal to R Thevenin. This is known as the maximum power theorem. When R Thevenin is equal to RL, or RL is equal to R Thevenin, then only the power is maximum. So this is also called as maximum power transfer theorem. Now next, we have an example. Find the value of RL for the maximum power transfer in the circuit of shown in figure. Find the maximum power. So this is a circuit between terminal A and B. There is a RL and this is your main circuit where we have to find V Thevenin's and R Thevenin's. Then we have to find the maximum power. So directly maximum power we can't find without knowing the V Thevenin's and R Thevenin's. Okay, so just remove the RL and find the V Thevenin's and R Thevenin's first. Then keep the RL and find the maximum power. Okay, now R Thevenin's. How to find the R Thevenin's? Remove the RL. See from this side, from the left to right, we have to just solve the this circuit. And for solving the circuit, you have to make power of the sources. Power of the sources means 12 volt source. Voltage source is short circuit. Current source is open circuit. So this short circuit is here. Then 6 ohms and 12 ohms will be in series. Now in open circuit, this 2 amperes, it will become open here. So these 3 ohms and 2 ohms will become in series. So the 6 ohms and 12 ohms will be in parallel. Then whatever the result is coming, these 3 will be in series. So 2 plus 3 will be in series. Then 6 ohms and 12 ohms in parallel. That is nothing but 6 ohms into 12 ohms divided by 18 and 4. This become 4. So 4 plus the 3 plus 2. 6, 7, 8, 9 ohms. So this is 9 ohms is the Rn. In one step you got the R Thevenin's or R Nortons. Anything is same. So next we have to find the what is the V Thevenin's. So across the terminals, remove the RL and open circuit this RL and find what is the voltage across this A and B terminal. So across the A and B terminal, we have to find the V Thevenin's, and these 2 ohms will not come into picture because it is an open circuit here, because we are open circuiting here and these 2 ohms will not come into picture because current will flow in the closed path only. So now we got 2 loops here, the same circuit. We got the 2 loops, one is I1 and I2. So find the 2 equations, 2 unknowns, then you will get the answer for the VThevenin. Now what is I2? I2 directly we can have with this. I2 is equal to minus 2 amperes because it is flowing opposite direction. I2 is minus 2 amperes. Now find the first loop equation and substitute this I2 minus 2 amperes in that, and you will get the I1. Once you get the I1, what is here, this is open circuit, this current is not come into picture, and the voltage here is nothing but your VThevenin. Now we'll check. So minus 12 because current leaving, plus 6 and 12, 18 I1 minus 12 I2 because I2 also current is there. Now we know from the second loop I2 is nothing but minus I2. Now substitute, you will get I1. So I1 is nothing but, if you substitute in this, minus 2 by 3 is the I1 from these 2 equations. Now apply KVL around the outer loop to get the VThevenin across terminal A and B. So it will be minus 12 plus 6I plus 3I2 here, outer loop. So this one, because 3I2, 2 into 0, there is no resistance here, 2 into 0 plus VThevenin. So then you can find VThevenin as the 22 volts. Outer loop, to find the VThevenin, it's not for the mesh analysis, it is for the finding the VThevenin. So VThevenin is now 22. Now we got, for maximum power, RL must be equal to RThevenin. So what is RThevenin? We got it here, 9 ohms. So RL will be same 9 ohms. So power equation is P is equal to V square by I square R, and that is nothing but V square by 4 RL if you substitute. So it is 22 is the voltage power 2, and 4 is the multiplication, and 9 is the RL, that is RThevenin. So 13.44 watt is the maximum power that can be delivered to the circuit, not more, not less. It is that point where RL is equal to RThevenin. This is the power, peak power we'll call. So this is how we'll find the maximum power. So we have some problems also, practice problems, where I use 2 problems for superposition, these 2, and 2 for source transformation. Answers also given. Now another 2 questions for the Thevenins, these 2, and 2 questions, 1 question for the Nortons and 1 question for the maximum power. So you can find it. Okay, thank you for chapter 4 is finished now. In chapter 5 we'll study about the another passive elements, inductance and capacitance. We'll see that one. Okay.